Hello, my name is Smrithi Surender, and I'm a third-year bioengineering major in Dr. Cocconi's Pediatric Rehabilitation Technology Lab. These are my teammates.
Hi, I'm Leah Nguyen. I'm a third year biology major.
Hi, my name is Miriam Contreras, and I'm a third year bioengineering major.
Hi, my name is MacAluso. I'm a first year bioengineering student.
And this is our project, a pressure detection insole device to provide auditory feedback during gait for children with cerebral palsy.
So, cerebral palsy is a disorder due to a defect or lesion of the immature brain. It can be classified into different motor deficits characterized by the lack of control and coordination of muscle and limbs. Delayed acquisition of developmental milestones may result in disturbances of the sensations. Communication and social interaction skills may also be affected. Additionally, cognition and perception may be affected as well, restricting learning and behavioral development. Limitations imposed on their ability to move and explore the environment result in a reduced experience of the world, affecting their development. And at the moment, many devices to assist or rehabilitate motor functions are designed for use only in the clinical setting or are very expensive. For these reasons, rehabilitation devices can be inaccessible to many patients who need them but cannot afford them or are unable to go to a clinic. Some devices are unsuitable for home use or lack patient engagement. At-home rehabilitation devices are important as they allow for more convenience and comfort than a clinical setting, and may even be more engaging or motivating for the patient. With the idea of at-home uses in mind, we found that rhythmic auditory cueing can enhance gait performance and stability in those with cerebral palsy by inciting neurophysiological and musculoskeletal changes to enhance motor function. Our goal with this project is to develop a pressure detection device to provide auditory feedback during gait that can easily be set up by the patient and used in the comfort of their own home. In order to make this device work, we first have to understand how walking works and certain metrics that can be used to measure it. Bipedal gait is the way in which humans walk with two legs, and cadence is the number of steps per time unit, or to put it simply, how fast they walk. The action of walking can be split up into many different phases, focusing on only one foot and one phase at a time. We start with the stance phase, which is when the foot is in contact with the floor. The foot will first come into contact with the floor during the heel strike, which is, as the name implies, the heel of the foot strikes the ground. Then, as you put most of your weight on your foot, that would be the mid stance, and it is when your foot is flat on the ground. Then, for limb advancement, there's the toe off, where the person pushes off the ground. There, the foot goes into the swing phases, where the foot is off the ground and moves forward until it does another heel strike, and the cycle continues.
As mentioned before, the primary phases of bipedal gait are the stance phase and the swing phase. However, when a child is diagnosed with cerebral palsy, there are noticeable characteristics that affect the way in which they walk. One characteristic that is noticeable are gait abnormalities. Referencing the image, you can see with the image in the top right, the child's right knee is bent during the child's walk. And at the image at the bottom left, you can see the child's foot is angled abnormally. These complications do have a great impact on the stance and swing phases. With regards to the stance phase, some noticeable effects are a decrease in the walking speed of the child, their cadence to be much slower, and a decrease in stride length. These limitations put more stress on the child, making them spend more time in the stance phase than normal. For the swing phase, the child experiences a harder time getting his or her feet off the ground, resulting in a shorter period in which the feet are in the air. This can also result in the sliding of the feet. Although CP is not curable, we hope to reduce these limitations to a minimum and promote a healthy gait pattern. In the next slide, we will present a video of a child that is diagnosed with cerebral palsy and how the characteristics mentioned affect the child's development while walking. Moving forward, in order to determine the degree of the child's condition and to determine who our device will be most effective for, we reference the Gross Motor Function Classification System, also known as GMFCS. The Gross Motor Function Classification System contains 5 levels which increase in severity of the condition and focuses on the child's movement such as walking, running, sitting, and whether or not the child utilizes the use of mobility devices. With our device, we want to primarily work with children that lie within levels 1 and 2. For children categorized in level 1, they're able to perform everyday functions like walking, running, or moving in different terrains. The only challenge they possess are their motor skills, which are hindered like speed, balance, and coordination. Moving along to level 2, the gross motor skills are still functional, but the duration for which they are performed is reduced. Also, the need for assistance is not necessary. However, some may utilize it when walking in different terrains, like walking up the stairs, using the railing as aid. For both groups, we hope to work with these types of children, knowing both groups need little to no assistance when walking, and we hope to promote a healthy gait pattern, which can promote a child's activity and social interaction. Moving to the next slide, Miriam will go more in depth about the development of our design.
Following is an overview of our methods used to develop our device. Our prototype can be explained in 3 parts. First, it's the insole pressure sensor, which will slide in the shoe of the patient to obtain pressure readings. Here is a demonstration on how the device would be mounted on the patient's foot, and this is how the insole would fit on the patient's shoe. The second part is the auditory output and the microcontroller component. Here we have the components that will activate when pressure is sensed and therefore play a music beat which will incentivize the child to walk more. Then for part C, it's the feedback loop. Our feedback loop is designed to interpret the readings from the pressure sensor into an algorithm to play a corresponding feedback. I will explain more in detail each part in the next slides. When designing the pressure sensor component of our device, we had to consider the amount of pressure sensors needed to get an accurate pressure reading of the feet. At first, we only used one pressure sensor at the heel of the foot. However, we realized that this is not optimal to detect walking in children with CP because 1, this population has a tendency of walking with their tippy toes, and 2, by using a sensor at the ball of the foot, we can detect push-off, whereas the heel sensor can only detect heel strike. Another consideration of these sensors is that we do not want them to move when the child is walking, which will cause inaccurate readings. Also, we do not want direct contact when they're being used. Therefore, we 3D printed a thin insole with pockets for the pressure sensor to be in, and for extra protection, we glued the sensors. In the figure below, we can see the design of our insole and where our components and wires are located. When we are ensuring that all the wires are properly hidden, and we're ensuring this so that the child is safe. Then for the next part, we focused on creating the circuitry and the other devices and creating the Arduino code to get our desired output. All our electrical components are going to be secured in a 3D printed pocket that will attach to a Velcro strap. This will go around the lower calf of the child. Then we will try to find small electrical components so that our device is lightweight and small. For the microcontroller, we use the seed shell controller because it is small as a quarter, yet it's more powerful than an Uno Arduino. Then we decided a lithium battery because they are rechargeable and are more safe to use. Also, the charging mode was incorporated into the board in order to charge the battery and also ensure that there is nothing wrong with the battery. And lastly, we decided to go with this speaker because it's small, but yet it's really loud.
So our device will operate on a feedback loop in order to analyze the pressure applied by the child on the ground while walking. Leah, can you please click next? Yes. This pressure is then detected by the thin film pressure sensors and interpreted by the Arduino algorithm. If pressure readings are below the threshold and if there is an irregular pattern, then the verbal feedback will begin. Examples of this verbal feedback include, good job, remember to use both feet. Remember, balance is important, or no tippy toes. If the pressure readings are above the threshold or of a regular pattern, then light tone music that is known to have uplifting effects will play. We actually have a sample of her music, if Leah can play it for us. Thank you, Leah. After the feedback, the pressure sensors will still continue to input the readings and assess the improvements. Next slide, please. So far, we've been successful with integrating the pressure sensors and the auditory output. And here is a snapshot of our Arduino code where the pressure readings that we obtained with the pressure readings that we obtained from our prototype. In this graph, the dips represent where pressure was applied in real time. Here we have a picture of our current prototype. The strap with the speaker is the auditory output complex, and it's wrapped around the lower calf around 6 to 7 inches above the ankle. There's a black insole that can be slipped into the shoe in the lower image, and that has the wire coming out, which runs to the side of the foot. Because this insole can slip into any shoe, it is extremely compatible with almost any type of device or any type of home setting. It is also very low profile. The total weight of the device that we measured so far is only 80 grams, which does not cause any imbalances while walking. The Velcro straps also make it adjustable so that they can be worn on top of any brace or other prior assistive measures, like in the video of the child we observed earlier on. Next slide, please. A challenge that we faced was not being able to account for confounding variables like walking on the side of the foot. So we theorized that if there's no pressure detected on either sensor, and if the foot is on the ground, then the child is walking on the sides of their foot. Another challenge that we faced was not being able to monitor the pressure sensor readings in real time to ensure that the feedback loop is running as intended. In addition, we also suspect that the same tune will get repetitive over time. As a result, our future steps include exploring additional options for sensors, either adding more sensors or finding a sensor that encompasses a larger area of the foot. In regards to being able to monitor the device in real time, a Bluetooth mechanism may be able to solve this. Lastly, for music options, we want something that can change in pitch, tone, or frequency with improved gait. Next slide, please. We would like to thank Dr. Elena Cocconi for guiding us through every step of the process. We would also like to thank the members of the Pediatric Rehabilitation Technology Lab. We thank the Department of Bioengineering for the gracious support in funding our project. Lastly, we would also like to thank the Center of Robotics and Intelligent Systems for their resources. Thank you. Any questions?
Very nice presentation for this entire team of 4 of you. Yeah, you can stop recording.